First, does anybody have any questions about what we've been covering? Okay. So here's what we have going on. A week from today is exam 1. So Monday, 9/17. If you can't make it to the exam, to the night class, you can go to the day class the next day. So Tuesday, so this one is 6 p.m. S1326. You guys know that, but in case anyone's watching this video from the day class. And then if you guys can't make it to the night class, but you can make it to the day class, the exam is 2 o'clock in the room next door, S1328. Okay, so either one of those is fine. What if you went to both of them and took them both? I don't know. I've never thought of that before. That might fool my system. I don't know. Actually, you probably would just get whatever grade you got on the first exam I graded, whichever one that is. So I don't know. Let's try it. Let's find out. And the topics, it's going to be based on the practice problems from like 2 sets of practice problems. The units practice problems and the 1D kinematics practice problems. And I think I know I mentioned this before, but I'm just going to say it again. The way to use these practice problems is like this. You should, like before the exam, you should be able to, so here's what you should ask yourself. Can I do the following? Do these problems without looking at the solutions. And let's say justify every step in the problems. Okay, so it's not going to be enough if you just sort of remember how to do each of these problems. Like say the first time you do it, you can't get through on your own, so you look at the solutions, and then you just sort of start remembering how each step goes in the solutions, because the actual questions on the exam aren't going to be these questions. They're going to be related in the sense that, there'll be similar problems where if you understand why to make each decision at each step in the problem, you'll be ready for the exam question. You know what I mean? So it's not about just understanding how to do those specific questions. It's about understanding at each step why this is negative here and why you chose this equation here and stuff like that, okay? And what I would recommend doing is each practice problem, I would recommend doing without looking at the solutions at least twice, okay? If you do that, and as you do those problems, at each step you're thinking, do I know why I'm doing this, or am I just remembering that you do this here? And if you can do that, you shouldn't have any trouble with the exam, I don't think. In fact, so I taught the same class in the summer, and exam 1, the class median was, I believe the median of the class was 100%. Like half the class got 100% and half got lower than 100%, But if you don't do these problems, it's not going to go well, If you do the problems and put the thought into it that I'm saying you should, it'll go well. Okay. Any questions about the exam? And then, like, what most people who've contacted me have asked, Is there a problem set up that I've missed? So I haven't assigned anything yet. It'll probably be in about 2 weeks I'll assign the first thing, and then it'll be sort of more regular. But we have to cover enough topics that I can kind of combine topics and stuff for the practice problems to be the way I want them to be. So it's still going to be a couple weeks before anything's assigned that you have to turn in. So you should just be spending your study time like making sure you understand the notes, and then most of the time should be spent working on those practice problems. Okay. And tonight is the first actual lab of the class this week. It won't take too long. You should have time to work on practice problems after the lab's done, I think. All right, so now let's go on to instantaneous velocity. What we talked about so far was average velocity, and I think I mentioned that average velocity is actually not going to be that useful a concept to us. The reason I mention average velocity is because it sort of gives you an idea of what instantaneous velocity is. And instantaneous velocity is the one that's going to be important in this class. So you can think of this as we really only discussed the average velocity so we could understand instantaneous velocity. By the way, you know, a few of you said you ran the mile in track in high school. Let's see how much you guys know about track. I, when I was younger, held a world record for the 2 mile in track. Does anybody know track results well enough to guess what my average velocity was? World record average velocity in the 3,200 meters. Anyone know? That's a good guess, but that's not right. That's a good guess. Okay, so how about if I draw what happens in a 3,200 meters? You start here. It took, yeah, it took me longer than that. Takes some people 8 minutes, yeah. But to do a 3,200 meter, you take off here, you run around counterclockwise 8 times, and you end up right where you started. Anyone have a guess? Based on that, anyone have a guess of what my average velocity was? So yeah, average speed, if I was faster, would have been, if I was, you know, really fast, it would have been, what? Yeah, right. So I didn't hold this world record by myself. I tied the world record, okay? But the average velocity for my 3,200 meters was 0 meters per second. And it's because, you know, average velocity, just to jog your memories, is your position at the final instant minus your position at the initial instant divided by the elapsed time. Okay, so if the position at the end is the same as the position at the beginning, no matter what happened in between or whatever, the average velocity is going to be 0. Okay. And, okay, that was sort of a stupid joke, but, okay, so we're thinking mostly about the position versus time graph. And if an object's motion looks something like that, the average velocity from time 1 to time 2, remember, is the slope of the line that goes between them. Okay. So now let's talk about what the instantaneous velocity is. So again, if this is the position versus time graph, the instantaneous velocity is some kind of slope of this thing at a single point, okay? And so if you define this to be the point that you're interested in, okay, then the instantaneous velocity is the slope of a line that's tangent to that shape at this point. You can think of it as the slope of the curve at time t. And to define it mathematically, we're going to use that definition of average velocity. Okay, so the instantaneous velocity can be defined by approximating the slope at t by the slope, let's see, don't say slope, by the average velocity between two nearby points. Okay, so how would we approximate the slope of this line here? We take two nearby points. We'll call this one T1. We'll call this one T2. Okay. The average velocity then is the slope of the line that goes through these two nearby points. Okay. And you can see that the slope of that green line is pretty close to that slope of the red line. That's an approximation, right? How would you make that approximation better? Yeah, exactly. You just choose these T1 and T2 to be closer and closer to your value T, right? The closer you get, the better that approximation is. Okay, let's do an example. So say that our position versus time graph looks like this, and it's the function p of t is equal to t cubed. Okay. And say that we want to know what's the instantaneous velocity at time equals 2 seconds. Okay? Let's do this with 3 approximations. So first, let's make T1 equal to 1 and T2 equal to 3. Then the average velocity is, what's the position at time T2? 27. What's the position at time 1? And we're going to divide that by 3 minus 1. And so you get 13 meters per second. Is everyone following how I did that? Or anybody have any questions?
How'd you get 27?
Yeah. So yeah, the function here is to get the position, you just take the time and cube it. Okay. So when the time is 3 seconds, you take 3 cubed, and that's 27. And when time is 1 second, 1 cubed gives you 1, and so you get this. Okay. So now let's try to get a little better approximation. Let's say T1 is equal to, let's say, 1.9 seconds. And T2 is equal to 2.1 seconds. This should give us a better approximation because now, you know, our two like values, those two nearby values are a lot closer to the thing that we're trying to approximate. So the average velocity, 2.1 squared, well, I don't have the intermediate things here, but this should give you about 24.01. No, not 24. 12.01. Did anyone plug that in? I think that's what you should get. What? Yeah, okay. And then to get a better approximation, you could say T1 is equal to 1.99. And T2 is equal to 2.01. I'm just getting, like, bracketing that value of 2 seconds tighter and tighter with each one of these approximations. Okay, and each time I do that, that average velocity is getting closer and closer to the instantaneous velocity. If you do this, you get that the average velocity is 12.0001 meters per second. Yep. So yeah, in this case, you're right that 12 is what it would be. In order to get that value, yeah, right. You use calculus to get it, right. Sometimes it's really easy to see what it's trending towards, like in this case, because that's a, it's like a really, like, it's a function that behaves very nicely. It doesn't throw you any real curveballs, you know. Sometimes it wouldn't be that hard to see, but this idea of approximating it by choosing values that bracket your chosen value closer and closer and closer together is like the definition of that instantaneous velocity. Okay. And okay, so you get a better approximation as T1 and T2 get closer to T. Okay. In this example, the actual instantaneous velocity is 12. Okay, so there are a few things that you should notice about instantaneous velocity. The first one is that instantaneous velocity is defined by a single value of time. Okay, whereas the average velocity required 2 values of time to be defined. Okay. And this allows instantaneous velocity to be written as a function of time. Okay, so that's like the definition of a function. If you're given an input value, you can calculate an output value. Okay, you can think of this function as v of t. So that means that average velocity, you can't write that as a function of time. Instantaneous velocity, you can. Second, because of number 1 here, anytime you see velocity written as v of t, so anytime you see velocity written as a function of time, or just simply velocity, you should know that you're talking about an instantaneous velocity, okay, not an average velocity. Like anytime we're talking about average velocity, it'll say average. Anytime it doesn't say instantaneous or average, we're talking about instantaneous, okay? And the last one remember, we did an example where an average velocity and an average speed had different magnitudes. Like we had an average velocity that was 0, or I think maybe it was 0 in the example we used, but the average speed was some positive number. So these can have different magnitudes. Average velocity and average speed can have different magnitudes. But the instantaneous speed is always the absolute value of the instantaneous velocity. Okay, so that means that if you're given an instantaneous speed in a problem and a direction, okay, like say something's moving with a speed of 10 miles per hour in the negative direction, then you know the instantaneous velocity at that instant is -10, okay? Like the instantaneous speed and the instantaneous velocity always have the same magnitude. It's just an issue of one having direction attached to it and the other one not, okay? So, yeah, for example, an object with an instantaneous speed of 14 meters per second moving in the negative direction has an instantaneous velocity of negative 14 meters per second. Okay. And in kinematics problems, you're going to have to, recognize that pretty often. You'll be given an instantaneous speed, and you'll be given a direction, and you'll have to combine those to get a velocity. Any questions about that? Anything about instantaneous velocity?
If the direction, positive direction, then velocity will be positive?
Yes, that's right. Okay, so now the last thing we have to define before we can get to the main equations in this section is acceleration. And just like velocity tells you how quickly position is changing, acceleration tells you how quickly velocity is changing. Yep. Oh, really? Okay. Thank you. Okay, let me come back to that. Okay, so velocity tells you how quickly position is changing. Acceleration tells you how quickly velocity is changing. And so that's why the equation for acceleration is going to look really similar to the equation for velocity. It's just what was in the velocity equation was position is now going to be velocity in the acceleration equation. So acceleration is defined as the velocity at instant 2 minus the velocity at instant 1 divided by the elapsed time. That's equation 3. So do you notice this is the same form of equation I gave you for average velocity? It's just these are velocities now instead of positions. And these velocities, are these average or instantaneous velocities? Instantaneous, yep. And I'm not going to go into too much like intuitive stuff about acceleration. I'm just going to list out 3 things that you need to keep in mind about acceleration. So notice. The velocity equation that looked like this one was an equation for average velocity, right? This one I didn't make any distinction like that. Okay, and that is because, so for us, there's not going to be any distinction between average and instantaneous acceleration. So let's say average acceleration is equal to, we'll just call it acceleration, and that's the same thing as the instantaneous acceleration. And the reason for that is that we will only see constant acceleration problems. Okay, so if something has constant acceleration, then the instantaneous acceleration at any 2 points is the same thing, and so the average acceleration over the whole interval is the same thing. Okay, so that's why there's no distinction here. We won't be, we will be dealing with problems where the velocity changes, and that's why we had to make that distinction with velocity. The second thing to notice is in one dimension, non-zero acceleration means an object is either speeding up or slowing down. Okay, that's in 1D, and so it's pretty simple. Like if the thing is staying at the same speed, then there's no acceleration. Okay. In 2D, it's going to get more complicated when we move on to 2D. Non-zero acceleration can also cause a direction change. Yep. Just so if something's moving with a constant velocity, then the acceleration is 0. Like if you use any of these equations to calculate the acceleration, you'd get 0. If you calculate the acceleration and get anything other than 0, it means that the speed is changing. Any other questions about that? And then the last thing to keep in mind, this is sort of something to store away for later, because this is going to be a confusing thing when we get to 2 dimensions. Okay. And the last thing is, in 1D, if the velocity is equal to 0, the object has to be speeding up if, the acceleration isn't equal to 0. Okay. So no matter what acceleration it's doing, it's getting faster. If the velocity is equal to 0, it means it's at rest. So any acceleration has to make it speed up, right? If the velocity and the acceleration have the same sign, then the object is speeding up. And on the other hand, if the velocity and the acceleration have opposite signs, then the object is slowing down. Okay, and this thing, number 3 here, is maybe a little more complicated than you might think about, like how to figure out if something's speeding up or slowing down. You might think something like, if the acceleration's positive, it's speeding up, and if the acceleration is negative, it's slowing down. But you actually need to know the signs of the acceleration and the velocity to figure out if something's speeding up or slowing down. Okay? It's the relationship between those two values that tells you whether it's speeding up or slowing down. Okay? So, for example, if you had a car going this way, yeah, it's a good thing this car has such bad emissions so we can tell what direction it's going. And let's say that this is the positive direction. Then what do we know from this picture? Yep, exactly. The velocity is positive. So A positive would mean it's speeding up. And A negative would mean it's slowing down. And then on the other hand, let's draw the same car going the other way. And make the positive direction this way still. Then from this picture, we know that the velocity is negative, right? And so in this case, if the acceleration was negative, that would mean that it's speeding up. And if the acceleration were positive, that would mean it was slowing down. Okay. Any questions about that? All right. So I have a question for you. So just talk about this to each other for a second and see if you can make sense out of this. When something is thrown upwards into the air, is the acceleration pointed up or down? Okay? So think about that and talk to each other about it. And help each other understand it, like if you feel like you understand it well. Okay, so yeah. So the same way as like the acceleration in these examples, like if the acceleration was positive, it means this car is speeding up. Well, that acceleration points in a direction. You know, if the acceleration is positive, it means that the acceleration is pointed this way. Okay. Yep. And so it's really, this positive negative thing is really whether the velocity and acceleration are pointed the same way or whether they're pointed opposite ways. Okay. That's what those signs are getting at. That would probably help you in doing this. You really don't have to, but that would probably help. So just draw a picture and, you know, that's what I would recommend. Draw a picture.
But isn't it like in the eye of
Yes, but you're right. So you could do it, you could define your positive direction two different ways. You're exactly right. But the answer you would get about the direction the acceleration is pointing would be the same in either case. It's just it would be called positive in one case and it would be called negative in the other case. It's like really trippy. Let's think about it three ways. So first, let's think about it without. Yeah, let's think about it without any signs at all. Okay, just think about it in terms of something is slowing down if acceleration and velocity are pointed opposite directions, and it's speeding up if they're pointed the same direction. Okay, so when something's thrown up into the air, it first is going up this way and slowing down, right? We'll think of that as step A. And second, it reaches its highest point and then starts coming down. And as it's coming down, it's speeding up, right? Okay, so this is the velocity in both cases. If it's slowing down, that means the acceleration and velocity have to be opposite directions, right? So which direction is the acceleration? Yep. And now in the second part, it's speeding up. So do they have to be in the same direction or opposite directions? Same. And so it's down. And so even though the direction of motion, the direction of the velocity switches directions, right? The acceleration stays the same the whole time. Okay. The other way you could do it is by assigning a positive direction, you know. So like what if you chose your positive to be pointing up? In this case, your velocity is positive. It's slowing down, so your acceleration has to be negative, which means downward. Okay, it means the opposite of the positive direction. In this case, when the object starts to fall, the velocity is in the negative direction. It's speeding up, so the acceleration also has to be in the negative direction. Okay. And you could make the other choice too, just like you guys noticed. If your positive direction was down, what would your velocity be here? Negative. It's slowing down, so your acceleration would have to be positive, which would be downward. Okay?
And then so when we answer the question, we say it's pointing up or down. I still don't understand that. Because in one instance, it's pointing down.
In every instance, the acceleration is pointing down. It's just what changes is the mathematical sign. So now think of your positive direction like this. Okay. That means the velocity is negative, right? It's slowing down, so that means your acceleration has to be positive because it's the opposite sign of the velocity. And if the acceleration is positive and your positive direction is down, your acceleration is down. So it tells the same story either way, even though your numbers could be different. Any other questions? I mean, that's not something that most people are going to have just totally ingrained right from the start. That's something we're going to kind of grapple with for a while, probably. Yep.
Your car example, what
Mhm.
defines the velocity direction? Just the way you put it.
The velocity's direction,
The car, force actually.
yeah. Well, the velocity is the direction it's moving, you know. So if something's moving from here to the wall, its velocity is that direction. Okay. And then whether that's positive or negative depends on what I define as my positive direction. That's right. So the velocity was only positive because I chose my positive direction to be that way. Any other questions? Okay. So now we can get to the three big equations for this section. So the equations for one-dimensional kinematics and again, we're assuming constant acceleration. I'm going to have to define a couple things. What I'll call the initial position and the initial velocity. So P sub I and V sub I are the position and velocity at time equals 0. And what I'm going to call P final and V final are the position and velocity at time final. The first equation says V final is equal to V initial plus A times time final. That's equation 4. The second equation says position final is equal to position initial plus velocity initial times time final plus 1/2 A time final squared. That's equation 5. And then the last main equation for this topic says 2A times the quantity P final minus P initial is equal to V final squared minus V initial squared. That's equation 6. Okay, and these V initial and V final, are those average or instantaneous velocities? Instantaneous, yep, because they're happening at specific times, a single time. Okay, and now I'm just going to list out a few steps that you can follow for using these equations, and then we'll get to some examples. So steps for using the constant acceleration equations. The first step is you need to specify an instant corresponding to time equals 0 and an instant corresponding to time TF. Okay, you can think of this as time equals 0 is where you turn on your stopwatch. And time final is when you turn off your stopwatch. And then you also have to specify a location corresponding to position equals 0. And a direction corresponding to positive, or I'll just say positive direction. Okay. So in order to put numbers onto all these things, to use these equations, you have to define 4 things. Time equals 0 instant, position equals 0, positive direction, and time final. And how do you choose these? Well, the position equals 0 location and the positive direction, those aren't super critical. You can actually, in most cases, choose a lot of different values for those and still do the problem. But these first two, your time equals 0 and your time final, if you choose those wrong, usually you can't do the problem. Okay, so how do you choose time equals 0 and time final? So choose your time equals 0 and time final based on when you know stuff and when you want stuff. Okay. So like if you're doing a problem where something's launched into the air and you want to know like what the velocity of this object is when it hits the ground, you want to know something when it hits the ground, so that's automatically going to be your T final, okay? And if it gives you something about the velocity at the instant it's launched, or the position it's launched from, those are things you know at the instant of launch. So that's going to be your time equals 0, okay? Any questions about that? Okay, so once you choose these, list out the variables that you know and the variables you want. So I write this as a table, like know stuff that you know on the left side, stuff that you want on the right side. And say you have a problem where you're given in the wording of the problem the acceleration, the initial velocity, the final position, the initial position, and you're asked to find the final velocity. This is just an example, but then the third step is look for an equation. So one of those 3 equations I just gave you that includes the variable that you want, and every other variable in the equation is known. Okay, so of equation 4, 5, and 6, can you see any equation that would work with this set of variables? Let's see. We know, yeah, so equation 6 would work because V final is in equation 6, and everything else in equation 6 is in the known column, okay? If you look at, so let's look at equation 4. V final appears in equation 4, but the rest of equation 4, I guess there's no T final. That's the problem. That's why we can't use it. Okay, and the same with equation 5. Well, that one doesn't have V final in it, so you can't do it for that reason, and T final isn't known. So equation 6 is the only one that works there. Okay, and then I'll do a last step. I'll just call it star. You don't always have to do this, but on the harder problems, you do. If there isn't an equation that works, find an equation that lets you solve for acceleration or T final, okay? And then go back to step 2. So if you get to step 3, nothing works with the variables you have. Then in this case, acceleration is already known. So you know that the one you're looking for is going to be T final. So see if you can find an equation that'll let you solve for T final. Once you do that, T final will be in your known column. And now you can go back through and see if you have an equation that works. Okay. All right, so here's an example. Say that you have a car traveling at 50, actually, let's just do this in meters per second. So my question says 50 miles per hour, but let's just do that as 22.35 meters per second. And when it's at that speed, it hits the brakes. And say that it takes 30 meters to stop. The question is, what's the acceleration over those 30 meters? Okay, this is going this way. There's no emissions because it's a Prius. And it hits the brakes here, travels 30 meters, and at this point it's stopped. So the first thing we have to do is choose our two instants, our position that we're going to call 0, and our positive direction. Okay. So I said before that the most important choices are the ones for the instants. Okay. So what do we want to choose as our first instant? Our time equals 0. Yep. And we know the speed at that instant, and that's what sort of tips us off that that's where we want to choose to turn our stopwatch on. Okay. Because we want to choose instants where we either know stuff or want stuff. So our time equals 0 is going to be when the car hits the brakes. Where do we want to choose our time final? Yep. Yep. So we can say that a bunch of different ways in this problem, but they all correspond to the same instant, right? We could say after it's traveled 30 meters or when the velocity is equal to 0 or whatever. But that's the instant that's going to be our time final. The other two are sort of arbitrary. So let's say our position equals 0. Might as well make that the location of the car when it hits the brakes for the first time. Another way to say that is the location of the car at time equals 0. Okay, location of the car at the instant that we chose as time equals 0. And then the positive direction, if nothing else. So sometimes these choices can make the math a little simpler if you make the right choices. If there aren't any other indications, you might as well just make the positive direction the direction the thing is moving. So I'll just call this the direction of motion. Okay, so now we're done with step 1. Step 2, we're going to write out this table. So let's just go through a list of all the variables. I mean, here are all the variables that are possible. Time final, position initial, velocity initial, position final, velocity final, and acceleration. Okay, so let's just go through those and think about what we know already and what we don't know, what we want to find. Do we know a value for the time final? Like, we know what instant corresponds to, but do we know how many seconds it is? We don't know that. So how about initial position? Do we know the position when time is equal to 0? And what is it? We do know that. It's 0 because that's how we chose. That's what we chose as our position equals 0. So our initial position is going to be equal to 0 because it's sort of like a circular logic thing. It's going to be equal to 0 because we chose our 0 position to be the position when time is equal to 0. It sounds more confusing when you say it than it is. the initial velocity, do we know the velocity when the time is equal to 0? Yep. That's the one that's given, 22.35. Do we know the final position? Yes, we know that. That's 30 meters. I have it positive here. Should it be positive or negative? Yes, I just wrote that wrong. Thank you. So I have it positive. Should that be positive or negative? And why is that? Yeah, right. We set the positive direction in the direction of motion. And then the final velocity, do we know what that is? It's coming to complete stop, so that's going to be 0. And then the last variable is the acceleration. Do we know that? That's what we want to find. Okay, so now look through those 3 equations and see if there's one where there's one that contains acceleration and everything else in it is listed here. Okay, yep, I think it's equation 6 again. So 2a times, I'll just write out the whole equation first. Okay, so 2a, that just stays like that because we're trying to solve for a. P final is 30 meters. P initial is 0. V final is 0. Minus V initial is 22.35 meters per second squared. And on this first exam, I'm going to want you to keep all your units in these calculations. I'll take off, I mean, it won't be like a horrible amount of points I would take off, but I'll take off points if you don't keep your units. After the first exam, we can relax that, but I want you to get used to doing that like you could do it if you had to. So multiply this through and you get 60 meters times A is equal to negative, if you square 22.35, you get 499.52. I'll bet that's round off error, probably. And what about the units? Yep, you're going to square both of these, so you have meters squared over seconds squared. And so now to solve for A, you're going to divide both sides by 60 meters. So A is equal to, so now to do this division, I'm going to use the same notation I used for unit conversions. So we have negative 499.52 meters times meters over seconds times seconds. And we're going to divide that by 60 meters. Okay. So one of those meters cancels with that meters. And you end up with negative 8.33 meters per second squared. And so the units that you get are the correct units for acceleration. And that's a good sign that it's sort of a way to check your work. If you come out with your units not being what you expect them to be, like you're looking for a position and you get something with seconds in it or something, that's a sign that you need to go back and find out where the mistake happened. Okay? Any questions about that? Is this plausible? Negative 8.33 meters per second squared? Well, first of all, does the sign make sense? Does it make sense that we get a negative acceleration? Yeah, because our velocity was positive, our acceleration is negative, so it's slowing down, and that's what the problem's describing. How about 8.33 meters per second squared? Like, can a person live through that acceleration? Yeah, yes. That is less than, so 1 G is 9.81 meters per second squared. This is less than 1 G, so that's fine. If you get up to, I don't remember what the values, I think if you get up to 5 Gs and hold it for a long time, like sustain it for a few seconds, that can knock you unconscious. Yeah, and there are ways to, like, apparently, I think I saw some like PBS special on fighter pilots, like while I was waiting for Friends to start or something once, and like fighter pilots, when they go into a really sharp turn where they're going to be pulling a lot of G's, they push, like, force really high pressure in the vessels in their head, because the danger is, the reason you pass out is that high acceleration makes the blood drain out of your brain, and that makes you pass out. So if you can force that blood to stay up in there, you can avoid passing out. So yeah, if you stay, an acceleration of under 1 G anyways is very sustainable. Any questions about, oh, and I never went back and did the speed thing I said I was going to do. So let's, this will be fast. This is out of order. Average speed. So average speed is equal to, I'll call it S sub average. And that's equal to the distance divided by the elapsed time. Okay, so the average velocity, remember, was the displacement divided by the elapsed time. The speed is just the distance divided by the elapsed time. So I never tied the world record for the average speed in any track races. I was pretty far from that, but I still got that velocity thing going for me. But yeah, like if you, so if this is Minneapolis and this is Iowa City or something, and say that this distance is, how far apart are those, 300 miles or something? Okay, and say that you drive for, say each way takes 4 hours. Then define this as your 0 position, you know, choose some positive direction, let's say towards Iowa City. Did I say Des Moines or Iowa City? Okay, good. So this is Minneapolis. This is Iowa City. The average velocity would be, so you would go, so I'm talking about the average velocity for the whole trip, and say that you go here, and after you get there, you turn around and come back. Okay. So the average velocity is going to be 0 minus 0, because the final position is the same as the starting position, and they both happen to be my 0 position, divided by an elapsed time of 8 hours. So you have an average velocity of 0 miles per hour. The average speed is, in the numerator, the total distance traveled. What's the total distance traveled? Yeah, right. 600 miles divided by 8 hours. And I believe that is 75 miles per hour. Any questions about that? Okay, so these don't have the same magnitude. I said something about these having the same magnitude, just possibly different signs. Do you remember why this can be, and how does that relate to what I said about them having the same magnitude? Okay, so these are average speed and average velocity. Those values can be totally unrelated to each other. It's the instantaneous speed and instantaneous velocity that are always the same magnitude. They're either the same or one is negative and the other one's positive. Okay, any questions about any of that? All right.